Um, Recently, probably earlier this week, there was a news article. So there was a small child using stem cell treatment had his windpipe recreated using stem cells. That stem cells, now what happened was, as a baby, the windpipe was too small, and because of a rare disease, while the rest of the body was going to grow, this region was not going to grow. And so that means sooner or later there'll be insufficient air and the child is going to die. So they did this stem cell treatment to regenerate the thorax, okay, the windpipe. And it now turns out that after 2 years, it has grown out to be a living thorax, which can be completely replace the original problem. And now the child has survived for 2 years, and the diagnosis seems to be that that kid is going to grow up to be a normal human, a normal adult. And so that's a major, that's the first major example of in the human being, right, an organ being regrown completely. And so the thing is that maybe with over time you can have more complicated organs be grown over that, and maybe this technology becomes obsolete at that time. But in the interim, maybe this is potentially a solution for the next 10 20 years. That's what we think, if it is successful. I mean, it's still not a completely commercially viable product, but it has received enough investment to try to take it to the next stage of testing it out on animals and human beings. And if it is cleared over, usually in those cases it will be tested on patients who have little other option left to live, and then they'll go from there and and build it off from there. Yeah. So a lot of possibilities. You will see from Igor's presentation some ideas related to medical devices. You will see in Sheril's presentation something about energy storage, and so, and then each of you are going to provide some other examples on catalysis, on structural properties of zirconia synthesis, clay nanoparticles, and some porous structures. Okay. We talked about aluminum nitride. Do you remember what are some interesting properties of aluminum nitride? Pardon? Yes, so it is electrically resistant but thermally conductive, right? So thermal conductivity is high, electrical conductivity is low, and so you would use that for a package, right? Also, the coefficient of thermal expansion is very low and similar to silicon carbide and silicon materials, and so it is useful for packaging applications. We wanted to try to use nanoscale aluminum nitride mixed with microscale aluminum nitride, so bimodal, right? Large particles, you fit small particles in the middle of them, right? And then you see you increase the packing density, right? Because microscale aluminum nitride itself only fills to about 52 volume percent of space. Nanoparticles, on the other hand, because of their electrostatic repulsions and agglomeration, they don't fill more than about 40 volume percent of space, right? So the idea of nanoparticles which pack poorly, increasing the packing density of another powder that packs poorly, hasn't been tried before, right? Those large spheres and small spheres that I showed to increase, as an example of particle size distribution, increasing packing density that I showed, were for particles that are typically tens of microns and a few microns. For them to be in the nanoscale range, not a whole lot of work has been done before. And so we were able to try to look into that. Work done by one of my students, Valmeganathan, and a couple of other students. Nathan is working with Intel Corporation after finishing his PhD now, since last year. And what he found out was, this is in weight percent, what is the maximum content of the powder in the polymer. Okay. What is plotted here is the ratio of micro to nanoscale particles. Okay. So two things you can observe. If you change the ratio of micro to nano, the maximum packing density changes, and it goes to a case of around close to 91 weight percent, which turns out to be close to 72 volume percent, right? So you had one powder that had a maximum packing density of about 54 volume percent. You filled it with another powder that had a maximum packing density of about 40 volume percent, but the combined mixture in some ratios allowed you to get close to 72 volume percent, which is really high for ceramics, right, used for injection molding. Here is viscosity plotted as a function of solids loading, right? If packing fraction increases, what did you learn in your when you were dealing with mixtures, right? What happens to when the packing fraction increases? What happens to the viscosity? Right, right, right. So now, what about the maximum packing fraction? If that increases, what happens to the viscosity? Right, we dealt with the critical volume fraction of powders, right? As it goes up, that phi c increases, and so viscosity actually goes down, right? And so this is what we saw. This is just the blue beads are just microscale aluminum nitride, about 0.8 microns aluminum nitride. Now if you fill the space with nanoparticles, right, you increase the maximum packing fraction. And so for any given packing fraction, you have lower viscosity for the bimodal system, right? As we had seen earlier, right? You increase maximum packing fraction, you will reduce the viscosity for any given volume fraction. As you increase the volume fraction, of course, viscosity will increase, right? So you have two possibilities now. You can either be at the same volume fraction of powder and just get better processability, or you can go all the way up to 72 volume percent, and so you can get much better structures in terms of controlling the dimensions when the material gets sintered. So you can control sintering shrinkage, right? So this is going to appear in press shortly, and it has come across in a couple of different conference papers up to now. Okay. So then the idea that we looked at when you were looking at processes was you take some powder, right? It has good flow properties. So now you try to create a shape, you injection mold a shape, right? And then you remove the polymer. You want to see what happens when that occurs. Then you want to sinter the materials, right? And you begin to connect the particles together. You have some grain growth, and then finally you have a dense part which has some shrinkage, right? What we were looking for was if you go from purely microscale powder to you going to a bimodal micro nano mixture, because you have higher packing density, can you take advantage of the improved rheology and get lower sintering shrinkage as a result of these additives? Okay. So we went ahead and tried to do some debinding. There were some differences over there. We saw rheological differences already, right? But then the next thing that we looked at was how does this material sinter? So this is just a microscale aluminum nitride. We added yttrium oxide, to form a liquid phase. You know that alumina and yttria form a glass, right? So we used about 5% yttria. The yttria we used were nanoparticles. Okay. One thing about nanoparticles is, as you reduce the size, it turned out that the melting point gets depressed because of the increased surface activity. Okay. So at when you push the materials to the nanoscale, the liquid forms at a lower temperature. We wanted to see if the sintering additive was nanoscale and the liquid forms at a lower temperature, can you sinter the material at a lower temperature? Okay, that was one thing we wanted to look at. Then we said, okay, if we add some nanoparticles of aluminum nitride to that mix, will that go ahead and reduce the sintering temperature further? Right? You'll begin to see that there are some interesting formations such as nanorods over here. You know, this is about 2 micron in dimension. You can't see it very clearly on the screen. So the same 2 microns over is what you end up seeing over here. And you can see that these rods that are beginning to develop are in the nanoscale. When we did a chemical analysis of just the regions with the nanorods, we found that it had yttria and alumina as the constituents. So that is the liquid phase forming, and when it is then beginning to solidify, it seems to, for some reason, make these kinds of rod-like structures. Okay. With the micro nano aluminum nitride, we ended up sintering this material unto the point where around 1500 or so it begins to show a good amount of densification. You can see individual particles, and there are some necks, interconnections that are beginning to form, right? And a little bit of grain growth that's occurring. Yes? They're all about 2 microns, roughly. What we think is there's some amount of melting that has already occurred in the in-between, and it's filling up some of the spores. Okay? And there's maybe some dissolution of the aluminum nitride. That's possible. That's a good thing. Okay? Main thing was this nanorod that we could see in the micro scale, we could not see when in the micro nano mixtures. And it is possible that the capillary effects end up holding the liquid very tightly and limit some of the reprecipitation. Either that, or a lot of aluminum nitride in the nanoscale begins to dissolve easily into the liquid, and so maybe some of the nanorod formation is suppressed. Okay. But the main thing was liquid phase was forming at a temperature that was about 100 degrees lower than what anyone has reported earlier. Okay, so we could see it at 1500, and maybe it occurs a little bit earlier, and that's some thermal analysis that we have to do to find that out. Okay, so some of that has been appeared this year in Ceramics International, and this is what it looks like as a fully dense material at 1650 degrees centigrade. And for that type of sintering around 1650, you end up having a shrinkage of about 14% or something like that. This is the literature values. Typically, you end up getting this is our study over here, and these are all the literature values for aluminum nitride. And very commonly, right, you have much lower volume fraction as far as packing goes, because no one has studied the micro nano combination before, and correspondingly no one has also tried to use nanoscale yttria for densification. As a result, most of the places which talk about sintering talk about at least 100 or 200 degrees more in temperature. So we are sintering at a lower temperature, and we are getting lower shrinkage because of the higher initial volume fraction of powders. Okay? Yes?
While having the sintering with the side of nanoparticle, was that effective? There was an agglomeration in it?
So what we found was the agglomerates could break down in the twin screw extruder when we mixed it, and that allowed us to get the very high volume fraction. We have to do additional experiments in this region to understand a lot of but you can see from this microstructure of the fractured surface that it is 99+% dense. There's almost no porosity over there. Right? So some benefits of working with nanoparticles: you can sinter them at a lower temperature. Okay, if you use a nanoscale liquid forming aid, the sintering occurs at a lower temperature, and then you get some nanorods. But mainly, if you use a combination of microscale and nanoscale, you can have lower sintering shrinkage and still get full density. Okay.